In this lecture, we will be examining the topic of alternating series convergence. Recall our alternating series definition. We have a series of the form sum n going from 1 to infinity of some power of minus 1 times positive term, non-negative term bn. And the idea, however we index it, is that we have a sign change every term. So we have a plus, minus, plus, minus, plus, minus. When we think about series convergence, the central question, in particular for a sum of positive or non-negative terms, is do the terms approach zero fast enough as n goes to infinity for the sum to be finite? The terms going to zero is not enough. That's kind of the central issue. The terms must go to zero fast enough. And we have the same kind of issue with alternating series, but we have different types of convergence. So we assume that our terms of our alternating series do in fact go to zero. So recall our alternating series, we have the sum n going from 1 to infinity of minus 1 to the n plus 1 times b sub n. Let's assume the b sub n's do go to zero so that we may have some kind of convergence for the series. And we noted that the first thing we do is check for this strong type of convergence, which we defined as absolute convergence. So we check the sum of the absolute values of the terms, which removes the alternating signs plus, minus, and turns everything to plus. And if that series converges, we say our alternating series is absolutely convergent. So you can think of this as removing the cancellation effect that can happen with the plus minus and see if you just turn everything to positive terms, does the sum converge? And this is the strongest type of convergence for a series. We call it absolute convergence. The issue becomes, what if you have an alternating series that is not absolutely convergent? Is there still a chance for some kind of convergence? And there is, and we call it conditional convergence, which we will formally define on the next slide. But the way to think of it is the limit of bn goes to zero, but the series sum n equals 1 to infinity of b sub n diverges. So we don't have that absolute convergence. Is there something weaker? And that would come from the idea that we have cancellation. So b1 and b2 are non-negative terms, so there's some cancellation here when you subtract one from the other. You get something similar when you subtract b4 from b3. You get something similar when you subtract b5 from b6. So does this situation where the bn terms are going to zero not fast enough for absolute convergence, but still you get this cancellation happening, does this give us some kind of convergence? And that's this conditional convergence. So we say the alternating series, the same alternating series we've been looking at so far, sum n goes from 1 to infinity, minus 1 to the n plus 1 times bn, where the bn are non-negative, is conditionally convergent if it is not absolutely convergent, which is important. We want to make sure that it doesn't have that stronger convergence. So if it is not absolutely convergent and it satisfies the following three conditions. First condition, all the bn are non-negative. We kind of get that for free here because the way we define this, the bn are non-negative. Bn plus 1 is less than or equal to bn for all n after some capital integer n. Another way to put that is that the b sub n are monotone decreasing. And finally, the limit as n goes to infinity of b sub n equals 0. So the terms themselves go to 0. If our non-absolutely convergent series satisfies 3 conditions, we say the series is conditionally convergent. And it is a weaker type of convergence than absolute convergence. And the process of checking an alternating series for this type of convergence is called the alternating series test. So how do we use this? Anytime you see an alternating series like this is the procedure we should use to determine if it converges. First, you test for the strongest convergence. We use the absolute convergence test to check if it's absolutely convergent. If it's absolutely convergent, you're done. That's the strongest type of convergence. We stop there. 2, if the series is not absolutely convergent, we use the alternating series test from the previous slide to check for the weaker conditional convergence. If it passes the alternating series test, in this step, you conclude the series is conditionally convergent and stop. 3, if we fail both tests, then we conclude that the series diverges. And an analogy here we can use is, imagine if you were testing people with some type of strength test, say a bench press, and you wanted to do as little testing as possible to be efficient with your efforts and your time. And suppose the 2 strength tests were bench press 100 pounds or bench press 50 pounds. So first here, the first step is you test for the 100-pound bench press. If someone can bench press the 100 pounds, you stop, because that is the strongest test. If a person can't bench press the 100 pounds, then you give them a second test and see if they can bench press the 50 pounds. If they do, you see that they are in the second strength category. If they can't bench press the 50 pounds, they're in the third category. And so this is the kind of approach we want to take when we deal with alternating series. Let's look at an example. We have the sum, n goes from 1 to infinity, of minus 1 to the n plus 1 times 1 over n plus 3. So our first step is to check for absolute convergence. So let's take our series and look at the related series, where we take the absolute value of the terms. And this negative 1 to the n plus 1 term is always plus or minus 1. When we take the absolute value, it's always a plus 1. And so the resulting series is the sum, n going from 1 to infinity, of 1 over n plus 3. There's a couple ways we could look at this. We can use a comparison test, like the direct comparison test, or the limit comparison test, when we note, based on a dominant terms argument, that for large n, 1 over n plus 3, the dominant term in the numerator is 1, the dominant term in the denominator is n, so it behaves like 1 over n. So we're getting something that looks like the harmonic. And we know the harmonic series diverges. We also could note that if we write this out, the first term, and let's leave some space here, the first term, when n is 1, this is 1 over 4. When n is 2, this is 1 over 5. When n is 3, 1 over 6. 1 over 7. And we notice that this is actually the tail end of the harmonic series. So we could note, what if we made this into the harmonic? We would have to add 1 plus a half plus a third. But of course we can't do that without changing this. So let's also subtract it. And so what we have is this entire sum is minus 1, minus a half, minus a third, And then we can lump all of this together as the sum, n going from 1 to infinity of 1 over n. And again, we know this is the divergent harmonic series. And again, you could have used the direct comparison test with the harmonic or the limit comparison test with the harmonic. Both would work. Instead, here we just took this different approach where we rewrote this series as the divergent harmonic series plus a constant. So this means that because this series was divergent, our alternating series fails the absolute convergence test. So this tells us that the alternating series is not absolutely convergent. So we need to go to the second step and see, does this have a shot at the weaker convergence? Again, this is like saying we asked someone to bench press 100 pounds and they weren't able to do it, so we go to the 50-pound bench press. Test for the weaker strength. Here, we're testing for the weaker convergence. So again, since our alternating series is not absolutely convergent, we check the 3 conditions in the alternating series test. So the first condition is that the terms are non-negative, and we see this is true for all of our n. So check on condition 1. Condition 2 says the terms are monotone decreasing. So how does the n plus first term compare to the nth term? Well, we see our n plus first term, just take n and replace it with n plus 1. When we do that, we get 1 over n plus 1 plus 3, or 1 over n plus 4. And now, compare these terms. What's bigger? Well, n plus 4, we have a bigger denominator than we have here. And so we see the inequality goes this way, which is what we wanted. So bn plus 1 is smaller than bn for n equals 1, 2, 3, so on and so forth. So we get the second condition. And the third condition, the limit as n goes to infinity of the terms themselves without the minus 1 to the n plus 1. We have the limit as n goes to infinity of 1 over n plus 3, and we see that that is 0. So this means our series passes the alternating series test, and this means that that series is conditionally convergent. So this is an example of how to check the convergence of a alternating series, and in this example it turned out the series had the weaker type of convergence. Now let's take a look at the difference in these two types of convergence. We said we have this stronger convergence called absolute convergence, and a weaker convergence called conditional convergence. And the following two theorems really capture the difference between the two. First, we say a series is absolutely convergent. And notice we've written it here in a generic way, but we can think of this as the an being our minus 1 to the n plus 1 times bn. But we don't have to specify that. This result holds for any series that satisfies the absolute convergence test. But if we have a series that satisfies the absolute convergence test, such as the alternating series we've been looking at, and this sequence, C1, C2, C3, is any rearrangement of the terms from the series, then the series of the Cn is also absolutely convergent, and the two series converge to the same value. So the sum of the A sub n's is equal to the sum of the C sub n's. The point of this is that it doesn't matter how you rearrange the terms. You will always get the same sum. This is illustrative of the strongest type of convergence of the series, absolute convergence. The weaker type of convergence, conditional convergence, is kind of weird. And that's very well illustrated by this theorem. If our sum, n going from 1 to infinity of a sub n, and again, in this case, think of your a sub n's as the terms from our alternating series, negative 1 to the n plus 1 times bn. If this is conditionally convergent, meaning it's not absolutely convergent, but it does pass the alternating series test, and L is any real number, then there exists some rearrangement, C1, C2, C3, so on, of the terms from our series, such that the sum of that rearrangement of terms is equal to L. This means you can pick a number, a real number, out of a hat, and you can find a rearrangement of the terms from the conditionally convergent series such that the sum of those rearranged terms equals that number. You can get your series to converge to whatever you want by finding the right rearrangement of terms. So how does this work? We can take a look at this with a visual. So first, suppose we are given an L in the real numbers. We picked it out of a hat, and we want to do this rearrangement of our conditionally convergent alternating series to get the new rearrangement to converge to L. So first of all, because it's conditionally convergent, it's not absolutely convergent, which means the sum, n going from 1 to infinity, of b sub n diverges. That's infinite. We also know it passes the alternating series test, which means the limit as n goes to infinity of the b sub n's is 0, and the b sub n's are decreasing. And just to make this a little simpler, for this illustration, let's assume the b sub n's are all strictly positive. So let's draw our value L here on the number line. And let's actually write out some of our sum. So our sum, our alternating series, we have positive and negative terms. So suppose we know our positive terms are the odd indexed ones. So we have b1, it'll be minus b2 plus b3 plus b5 plus b7, and the even indexed terms are negative. Now, let's think about choosing some of the positive terms initially. Well, we know that if we just start adding up all of the positive terms, that will give us an infinite value because the series diverges. But what that means is we can take as many as we want, start adding them, and they will get us, there will be some point where we'll get just past L. Maybe b1 plus b3 gets us here. But b1 plus b3 plus b5 gets us just past L. Well, we've gone too far. We've overshot. So we have b1 plus b3 plus b5. So this is what we're going to stick with for our first three terms. But then maybe if we subtract, see, our first negative term is b2. So if we subtract b2, maybe that gets us here. So this point here would be that B1 plus B3 plus B5 minus B2. But now we want to jump back over L, and so we add the next positive term. So to jump back over, so this was our first step. And to jump back over, maybe we need to add B7. And so this value here is B1 plus B3 plus B5 minus B2 plus B7. And then we would have to leap over L again, which would mean we would subtract the next negative term, or we would subtract B4. And the idea is that you keep bouncing back and forth. But in doing so, you are building your rearrangement to get your series to converge to L. And that's the essence of how this theorem works and how we illustrate the difference between absolute and conditional convergence. And this will manifest itself in a theorem that we will use in the next lecture, which is called the alternating series estimation theorem. This will be a very handy thing to think of, this visualization. But this demonstrates the difference between absolute and conditional convergence. If your series is absolutely convergent, this doesn't work. You can rearrange your terms as much as you want, and you will always get the same value for the series. For conditional convergence, you have this weird result that you can do given a target L, you can find a rearrangement such that your series with that rearrangement of terms will converge to L.